Now we will move on to the second talk of our session, and that is Aomawa Shields. Please, Aomawa, if you may share your screen and tell us about your exciting work.
Okay, wonderful. Hi, everybody. My name is Aomawa Shields, and I'm an associate professor in the Department of Physics and Astronomy at UC Irvine. And I'm very grateful to Victor and Katja and Becky and the other members of the Exostar Redux committee for the opportunity to come back and tell you about my KITP visit and the scientific results that came out of that experience. So my whole family went to KITP from April to May of last year, and we had a blast. I introduced my daughter to the beach for the first time while we were there, and we had to go every day because she loved it. And we had fun exploring the KITP residence rec area and playground and the basement where the piano was and the neighboring Santa Barbara playground. And with the exception of breaking my foot, it was a fantastic experience, and that only happened the last few days. I don't even have pictures of my foot or the immobilizer. But yeah, we had a great time, and we still talk about it today and look forward to returning. We are living in a whole new universe now, where once it was thought that the Earth was the only planet capable of supporting life. We now know of dozens of planets that may fit that bill. And the way that my group and the members of everyone from me to the other members of my group explore these potential climates and habitability is using a hierarchy of computer models, especially 3D global climate models. And these models have historically been used to predict climate and weather patterns on the Earth. And they're currently being used to forecast the global impact of anthropogenic carbon dioxide emission-induced climate change into the 2100s. But myself and a small group of others in exoplanets have been using these models to explore the possible climates of planets orbiting other stars. So a planet's climate is largely determined by its global energy balance. The energy balance between the incoming stellar radiation, what climate scientists typically refer to as shortwave radiation, so a little bit different than we astronomers think of that shortwave term. Everything that comes in from the star is referred to as shortwave, and the outgoing thermal or long wave emission. And so these two things have to balance, and if they don't, then the result is a change in surface temperature. And so this delicate balance is achieved through a combination of reflected, absorbed, and/or emitted shortwave and long wave radiation. And the global energy budget of the Earth has been calculated using a combination of numerical simulations and direct observations. And its partitioning is depicted graphically as what is known as a trend birth diagram. That's what you're seeing here. And trend birth diagrams have been valuable. Their analyses have led to a deeper understanding of all of the different ways that energy flows in from the star and is cycled through the atmosphere and surface of the Earth. These analyses have led to being able to quantify the effect of things like anthropogenic carbon dioxide-induced climate change, identifying sources of imbalance in the Earth system, and that's one of the most well-known. These trend birth diagrams have been used, have been calculated for other solar system planets, Venus, Mars, Jupiter, even Saturn's moon Titan, and one hot Jupiter exoplanet. They've never before been calculated for rocky, Earth-like planets orbiting different types of stars. In particular, the effect of starlight, of host star SED, on the planet's ability to maintain global energy balance and on the way that this partitioning changes has not been explored before. And so that's what we did. And of course, as everyone knows, different stars emit radiation across different wavelengths of the spectrum. And stars aren't the only aspect of the stellar planetary environment that are wavelength dependent. We know of atmospheric gases, of course, that are, and climatic feedback, such as ice albedo feedback. And so one of my earliest works was looking at the impact of host star SED and ice albedo feedback on planetary climate, because water ice has this unique property where it's quite absorptive in the near IR and infrared and extremely reflective at higher wavelengths, visible and shorter wavelengths, visible and near UV. And that has implications for planetary climate, how significant planets warm or cool, depending on the fraction of ice that exists on their surfaces, how likely planets are to enter and or exit snowball states, etc. So what we did was simulate M, G, and F dwarf planets, and we looked at and identified the percentage of incoming stellar radiation, what I'll call installation, that was required to maintain a climate similar to modern day Earth. And so what you're seeing here is global mean surface temperature as a function of installation and percent of a modern solar constant. So 100% of modern solar is what Earth currently gets from the sun. And so we've got the M dwarf planet in red, the G dwarf in black because it shows up better than yellow, and the F dwarf in blue. And so here's essentially the Earth around the sun. And this dotted line is the global mean surface temperature of the Earth, 288 Kelvin. And what we see is that the M dwarf planet requires only 88% of modern solar to get to that global mean surface temperature, while the F dwarf requires 8% more, 108% of the modern solar constant. And so we calculated trend birth diagrams for each of these planets to look at more closely why this is. And so while the F dwarf planet, as I said, requires a higher installation to get to this climate, 108% of the modern solar constant, it also reflects a higher percentage of that installation. Its atmosphere in particular reflects a higher installation. 29% of what it receives is reflected by the atmosphere. That's 2% more than the G dwarf planet's atmosphere and nearly 12% more than the M dwarf planet's atmosphere. While the M dwarf planet's atmosphere absorbs more, 34% of what it receives, right, compared to 19% for the G dwarf and only 14%, 20% less for the F dwarf. If we look at the surface, the F dwarf planet reflects 16% of the short wave that reaches the surface. So 16% of what it gets down at the surface is reflected, and that's 5 and nearly 9% more than what's reflected by the surface of the G and M dwarf planets, respectively. Right. Whereas the M dwarf planet absorbs so much more of what it gets from to the surface. 93% of what makes it to the surface is absorbed by the surface on the M dwarf. So if we look at the climatic variables a little more closely, what you're seeing here is surface albedo and ice fraction as a function of latitude for the M, G, and F dwarf planet. What you see is that at higher latitudes where there's ice on all three planets, that ice has this higher albedo on the F dwarf planet. That's that water ice albedo effect, which is wavelength dependent. The F dwarf planet's receiving more visible and near UV radiation from its star. While the M dwarf planet has the lower albedo ice, and so as a result, it's got a lower ice fraction correspondingly. So the surface temperatures are warmer on the M dwarf planet at the higher latitudes than on the G and F dwarf planets. If we look over here at difference in specific humidity, so I've subtracted the F dwarf planet's specific humidity profile from the M dwarf planets, we see that where there's open ocean on all three planets, that's in the tropics and the mid-latitudes, we've got a lot more radiation absorbed on the F dwarf planet compared to the M dwarf. And so we've got more specific humidity. This difference is negative. The F dwarf is warmer. And so that's resulting in slightly higher temperatures on the F dwarf compared to the M dwarf and G dwarf planets. Whereas in the higher latitudes, remember where there's ice on all three planets, we've got the lower albedo ice on the M dwarf is resulting in more absorption, greater humidity, and resulting higher surface temperatures in those higher latitudes. and that ends up reducing equator to pole temperature contrasts on the M dwarf planet relative to the G or F dwarf planets. So all three of these planets were rapid rotators, first off in our simulations, 24 hours, just like Earth. But of course, M dwarf planets are likely to be synchronously rotating if they're in their host star's habitable zones. So we calculated and created trend birth diagrams for a synchronous case around an M dwarf. And so this is where, of course, the substellar point is fixed with time. And what we find is that even though a similar amount of shortwave comes in, is absorbed by the planet in the synchronous case, there's much less shortwave actually absorbed by both the atmosphere and the surface. And that ends up at first causing lower surface temperatures overall on the day side, but then you have lower relative thermal emission by the day side. And so you end up having this kind of competing effect where we've got pretty high temperatures on the day side. We certainly get to above the freezing point of liquid water, but overall we see much lower minimum and maximum day side surface temperatures on the synchronous planet than the global mean surface temperature in the rapidly rotating case. And there's a couple of reasons for that. We know that weakened latitude, low latitude zonal winds and high cloud cover have been shown to cool synchronous planets relative to rapid rotators. And so here we have the incoming shortwave on the synchronous M dwarf planet, and we have this amount that's absorbed by the atmosphere and the surface, right? Not very much correspondingly, in that we have quite a lot reflected by those clouds, the weakened latitude, low latitude zonal winds, cool as well. Because not very much thermal emission, because there isn't very much thermal emission relative to what's absorbed, we do have warming on the day side, but overall a much cooler day side surface maximum and minimum surface temperature compared to the rapidly rotating case. So I hope that you will want to read more about our study than I can explain in 12 minutes. So here's the paper in APJ letters. The take-home points: host star SED heavily influences the energy budgets of Earth-like rocky planets. And as a result, we find the M dwarf planet requires less installation than the G dwarf planet to cause a climate similar to modern day Earth, while the F dwarf planet requires more installation. And this is due to the spectral dependence of water ice, albedo, as well as atmospheric gases like CO2 and water vapor, which have strong absorption in the near IR. However, synchronously rotating M dwarf planets have this sort of lower min-max day-side surface temperature compared to the global mean that we see on rapid rotators, Earth-like rotators, due to weakened low latitude zonal winds, high cloud cover, and lower amounts of absorption relative to reflection on the day side. I'd like to thank my funding sources and other KITP Exostar participants. I recall having great discussions with Eric, Adam, and Phil while I was there. And I also want to thank Becky Dawson for offering and giving me a ride to the Exostar Associated Conference after I broke my foot, as well as collaborators on the paper and Trenberth and his collaborators as well for their input. Thank you all for your attention.
Yeah, thank you, Aomawa. That was really interesting. So if people have questions for right now, please either raise your hand or type it into the chat. And I think as a very quick question, I will take one that has already been typed into the chat. Andrew McWilliam would like to know whether these GCM models that you're using actually include heat input from the stellar or solar winds.
Good question. No, these don't include any sort of stellar activity effects. What we do is we input the host star spectrum by specifying various percentages of flux across about 12 wave bands that are input, but there aren't any stellar activity or flare effects unless they're particularly specified as increased fluxes in various wavelengths, which of course, flare activity is quite variable, as well as, I'm sure, the solar wind properties. So that's not by default incorporated in the GCM.
Okay. If people have other questions on this topic in general, please type them into the chat to save them for later for the longer discussion that we'll have. And with this, thank you very much, Aomawa.